Hi, Mick McQuaid here for iste782 Visual Analytics. Today I'd like to talk to you about tidying data. So this is chapter 9 of our textbook. Our textbook is R for Data Science, and this is in part 2 of the textbook. So here's an example of what our authors mean by tidy data. So this is these are cases, tuberculosis cases in 3 countries over 2 years, and the populations of those countries. Here's an example of untidy data. It's the same information. It's not, the table isn't complete just to save space on the slide, but it's the same information basically. It's arranged a little bit differently so that the cases and population are now a type, and there's a count of each of those. This is untidy data according to the definition of our authors. And what I mean by untidy data will become clear in a minute. Here's another example of untidy data. It's the same information. The tuberculosis cases and the population have now been collapsed into one column of the table. And here's another example of untidy data divided into 2 tables. So here's a table that contains the number of cases over 2 years, and here's a table that contains the population of the 3 countries over 2 years. So the tidy case, the very first one that we looked at, is very much like first normal form in databases. Each variable has its own column, each observation has its own row, and every value has its own cell. The other examples violate these 3 rules one way or another, and so they're harder to work with in R as a result. Working with tidy data is comparatively easy. So, for example, here we compute the number of cases per population, per 10,000 of the population, as rate from the table 1. Think of the first table that we looked at as table 1. It's actually in the tidyr library. So once you've loaded the tidyverse package, you'll have access to table 1 as this. And if you look for a description of table 1, you'll find that the data comes from the World Health Organization. And oh, I'm sorry, I didn't. So we can compute the number of cases per year using count, and then we can visualize the change over time. And we do that using ggplot2. And so we have a point for the point estimate in the for each country for each year, and then a line drawn between those 2. And this is the output of that ggplot command. We could pretty it up a lot, and we'll talk separately about making graphics look better for presentation later. Most of the data that you get is untidy. Now, the authors use the terms untidy and messy interchangeably. I think that's a mistake, and they allude to that being a mistake near the end of the chapter. Because data is untidy for a reason, and messy is a pejorative term that implies that they just didn't think better of it. But data is untidy for a reason. So data is often organized to make data entry easier rather than for analysis. Data is often organized to make presentation easier rather than for analysis. And data is often aggregated, sometimes to persuade, sometimes to add value, and sometimes to disguise raw data. And if you have any familiarity with databases, you know that there may be storage or performance reasons to organize data differently from the notion of tidy that's needed for analysis. So we often get data in an untidy form and should expect that. How is data untidy? There are 2 main ways. One variable is spread across multiple columns, or one observation is spread across multiple rows. And these are commonly encountered problems that can be answered by two tidyr functions, gather for the first case and spread for the second case. So let's take a look at the tables that we looked at previously. So the tables that were divided into two, where we have the cases in one table and the population in one table, are in the tidyr packages table 4a and table 4b. So that cases table looks like this, and we can change it using gather so that we have 1999 and 2000 as part of the key year, and the value of that key is cases. So we've transformed that table into this one. So let's briefly look at that table again. So this table is harder to work with for data analysis purposes anyway. This table is easier to work with. We can do the same thing with the population table. That is table 4b. We gather the years and interpret the year as the key, and interpret the value of the year as population. Now suppose that you name the results of the previous operations tidy 4a and tidy 4b. You could then join them, saying left join tidy 4a 4b, and R will guess that country and year form a concatenated key to join them. Left join is supplied by the dplyr package, and you'll cover joins later in the course. Consider this just a preview of joining tables. So we can make one table out of those two tables. We can recreate basically the tidy table from those two tables. The second table that we saw above has a slightly different problem. So we have cases and population as a column, and count as a column. And what we would like to have is cases as a column and population as a column, and have the counts underneath them. So we basically want to take the last two columns of this table and turn them on their side. And that's what we do with the operation spread. So now cases is a column and population is a column. Variables can be combined or separated by columns, so it's possible to have two variables glued together in one column. We saw an example of that. And we can also have single variables that are torn apart into two columns, and we'll create an artificial example of that. So here's the example we saw, table 3, where rate is actually two different pieces of data, the tuberculosis cases divided by the population. And we would rather be able to do that as an operation to get the cases and keep those separately. So we can use the separate function to do that, to separate them into cases and population. So this is equivalent to the tidy table that we looked at first. Tidy is such a British word. It's not surprising that Hadley Wickham came up with this. He comes up with these like, well, these tables are tidy, Hermione. Okay, and we can separate an integer into parts. So we can use this separate function to separate the notice the integer has been separated into century and year here. And we can also put it back together. So if we put it back together, it's going to become characters, which is not great. Oh no, this isn't putting it back together. Here's putting it back together. But when we put it back together, it came back together as character. And the default separator is underscore. So we can change the default separator to not be underscore, and then we get the year back, but it's still as character, so we still have to convert it back to year. And we also have to deal with missing values. So values may be missing explicitly, meaning that they're tagged with NA, and values may be missing implicitly, meaning that they're not present in the data but not marked in any way. So here are examples of both of these. So we have, if you look at the first row, you'll see that there are 4 entries for 2015, but only 3 entries for 2016. And these are quarterly stock returns. So you see in the quarter row, we have the first 4 quarters of, we have all 4 quarters of 2015, and then we're missing the first quarter of 2016. So what we have for 2016 are the second through fourth quarters. And in the third row, you see we have the returns for these stocks, and we only have the returns for 6 of them. So the returns for the first 3 quarters of 2015, and we're explicitly missing the fourth quarter of 2015, and then implicitly missing the first quarter of 2016. We can make the missing value explicit. The implicit missing value can be made explicit by using spread. So we have stocks, year, return, and the result is that the return for the first quarter of 2016 is now NA. So whereas before it just didn't have a row in the table. And we can also make the explicit missing values implicit by saying na.rm equals true. That will remove all rows with NAs. So we can gather these, and now we only have 6 total rows, only rows for which we have values. We can also make the missing values explicit in another way using the complete function. So the complete function is going to return all combinations of year and quarter. And if it encounters anything missing a value, it just returns it as NA. So this is not quite the same as the NA we had before in the sense that this NA is introduced by the complete function. And sometimes we have NAs that don't really mean NA. So in this particular case, it means a continuation of Derek's entries. So we just didn't put, somebody just didn't put in Derek's name for all of Derek's entries. They just put a NA or perhaps put a dash or something in there. So another function that we can use to solve that is the fill function. So this fills NAs with the last filled value before the NA. Okay, so that's it for tidy data. For data analysis, you usually need tidy data, and it's your responsibility to put the data into that form because it's kept untidy for a lot of different valid reasons. And you can use all these functions: gather, spread, separate, unite, complete, and fill to make data tidy for analysis. And what I usually see happening is students use these in an ad hoc manner and don't keep a good record of what they've done. And that's a problem because then you get new data or corrected data in the original format and you don't know how you transformed it. And so you end up having to do a manual process again. So it pays to take a little extra time to document how you take data from untidy to tidy, because it is more likely than not that you'll have to do it again. Sometimes you get lucky, but in general, keeping your work in a reproducible format adds value to your work. So thank you for your attention, and till next time.